Hi everyone, it's Phil from My Math Teacher is Terrible. Thanks for joining. Today I have two interesting arithmetic questions. And why do I say arithmetic as opposed to math or mathematics? It's because there's a funny phrase between math teachers and kind of mathematicians, etc., that arithmetic is about numbers and mathematics is about letters. You'll see what I mean in a moment. But today there are two interesting arithmetic problems that we can actually use mathematics or our skills in certain parts of algebra to make the questions tractable. That is, like, easy to solve and solvable quickly. Okay, so the first one is, without using a calculator, calculate 106 squared. Okay, well, right away, we remember that 106 squared is 106 times 106. This is a big pain to do, right? If we do it the long way, it's kind of a pain to do. This is arithmetic. It's a pain. But this is where mathematics comes in to help us. Now bear with me, it seems unrelated. But let's actually look at a skill that we know from maybe Algebra 1, possibly the beginning of Algebra 2. We can recall that something like x squared is x times x. These are exactly the same thing. We're going to come up with a generalized way to do this. Right? We also remember that we can do something like x plus 1 squared. This is x plus 1 times x plus 1. Right? Whatever the number is, add 1 and then multiply it by itself using this rule. And what do we know about this type of expression, or the calculations that we do on this type of expression? Right? On something like this, we use FOIL, right? To write out what this actually is, or how we would calculate it, right? And F stands for multiply the first two things. X times x, x squared. O means outer. Multiply the outer things. This is the outer. X times 1 is x. I means inner. These are the inner ones. Multiply. Inner. X times 1 is x. And then L is last. These are the last terms. This one and this one in the binomial. 1 times 1 is 1. And then we see we have common factors here, or like terms here. And this turns out to be x squared plus 2x plus 1. Right? Because x plus x is 2x. And you're probably saying, dude, I could have already multiplied this thing by the time you talked about all this junk, which maybe that's true. But me, I don't want to do this, man. I would rather remind myself about this and then calculate it using this. So let's take this general thing and actually apply it to this. Well, I can actually generalize one more step. Let's do something a little bit more general than even this, where this is not a number. I'm going to do it way more generally. How about x plus a squared? This is x plus a times x plus a. Okay. This is very general. So using FOIL, x times x first, x squared. Outer, x times a is ax. Inner is also ax. And last, a times a. Right? Okay, and then let's simplify this in the same way that we did this one. We still have x squared. He has no friends. Ax plus ax is 2ax. And then the last one, a squared doesn't have any friends either. So there we go. So the very general thing, something plus something, turns out to be this. I mentioned in another video about like some ninja algebra tricks or ninja arithmetic tricks, dividing by 10, dividing by any power of 10, multiplying by any power of 10, etc. That idea is extensible to this. So how do this and this, how do they compare, or how are they related? First of all, whenever we're doing algebra, whenever we're doing mathematics with letters, right? Always remember that all of these things mean that a number goes in its place. So this looks crazy complicated until I tell you that x is 5 and a is 4. Then we can calculate it straight away. So always remember that. This is just saying that if I add two things and I want to square their sum, I could use this calculation. Or I could go through this whole thing. No problem. I could say x plus 7, and then it would be x plus 7 times x plus 7. Or it could be 3 plus 7. Now, 3 plus 7 is 10. I square it, I get 100. Why would I go through this? Because when it's like 472 plus 38, it's hard to square, right? And hopefully, as I said that, you see, or it crosses your mind that it could be related to this, because these are like inconvenient to deal with. I don't want to square this in this way using arithmetic. I want to square it using a trick. Okay, now the key to this, I just need to express this like something like this. The key to this is actually picking what I call convenient numbers, or picking a convenient way to break this up. Okay, so this relates to this how? Picking convenient numbers, right, as I said. So suppose I want to just pick this, I want to just divide it in half. So 106 is 53, right? 106 divided by 2 is 53. So I could, using this, I could say this straight away. I could say 53 plus 53 times 53 plus 53. Yeah, I could totally do that, right? 106 times 106. Then I could put this in here. But I have this like, right when I do the first, I have 53 times 53. Who wants to deal with that? I want to deal with that as much as I want to deal with 106 times 106. It actually doesn't help me, because 53 is not a convenient number. I want to pick a convenient number that I actually know how to multiply quite easily. So this is a okay first cut, but it's so inconvenient. Look how many times I have to multiply 53 by 53. Using FOIL, it's 1, 2, 3, 4. I mean, of course, once I get 53 times 53, I'll put it in the 4 places correctly. But still, it's a giant pain. Who wants to do that? Okay, so maybe not this one. Can I think of two other convenient ways, or one convenient way to split apart 106? Yeah, I sure can. How about something like this? 100 plus 6 times 100 plus 6. That's cool. Why? Things times 100, there's a shortcut for that. And then when I do the L part of FOIL, 6 times 6, very easy. I actually am not going to go from here to here. I'm not going to do that. I'm actually going to expand this using FOIL. Again, these are always numbers. Variables always mean there's a number in their place. Now we have a number in both places, right? I'm going to actually skip PEMDAS here. I'm going to skip order of operations, which says do this in parentheses first, because then we wind up here and we don't like it. But let's FOIL this. First, 100 times 100. 100 times 100 is 100 plus 2 zeros. Oh, outer. 100 times 6. Easy. 600, right? Inner, 6 times 100, also 600. Last, 6 times 6, 36. Oh my gosh, look how easy this is, right? Let's see. Let's add up the 600s. This is, so this is 10,000. 10,000 And 600 plus 600 is 1200 plus 36. Man, I could add this super easy. If I think about this, this is going to be 1236, right? 1236. Okay. 10,000 plus 1236. No calculator. I haven't picked this thing up at all. And now 10,000 plus 1236. 1, 2, 3, 6 can go right in there. 1, 1, 2, 3, 6. Oh my gosh. I didn't pick up the calculator once. I just used an idea that I already know and changed the context. Okay, let's see if the calculator agrees with my mathematics that I used to perform arithmetic. Let's see. 106 squared. 11236. Done! Super easy. So this goes to show you that foiling is not just for letters. We can actually use FOIL as a way to break down a more complicated multiplication example. I could put cubed to the fourth, whatever. There's methods for doing this no matter what this exponent is. It just happens that squared is pretty easy. And yeah, we can go ahead and use FOIL on this expression because here is a number and here is a number. All of this, the purpose of this is to show generally how I do it with two numbers that add up, that I add together. I did that here, but I broke it up in such a way that the multiplications were all convenient. I actually didn't scratch my head very much at all because I know that hundreds are easy to multiply regardless. And then I know something real simple like 6 times 6 is 36. I think that's very cool. And this is one of those kind of like lift by thinking about it rather than just going straight for ruining your lower back kind of thing, right? Lift with your brain instead of your lower back. Okay, so this is using FOIL. This is expanding something. The second question that's related here is, can I use the reverse of foiling, which is factoring, right? If I give you this, well, this one's a little bit difficult for algebra 1 or 2. If I give you this, you can come up with this by factoring, right? Okay, so let's think about this problem. And just like that, the whiteboard is erased. Okay, the second question I want to consider is this one. What is the greatest prime factor of 2 to the 12th minus 1? What is a prime factor? Let's do the prime factorization of 144. I don't know. 144. All right. Prime factorization is this thing, right? What is 144? Well, I know that 144 is 12 times 12. And then I know that the factors of 12 are 3 and 4. And I stop when I reach a prime number. Prime factorization, that's why it's called this. I certainly know that 4 is 2 times 2, and 4 is 2 times 2. What's the purpose of this, right? Usually at the end, we do something like this. We circle our prime numbers because we've reached the end of being able to factor them. And what we say at the end is 144 equals, well, I have 1, 2, 3, 4 2's, so it's 2 to the 4th power times, and I have 2 3's, so it's times 3 squared. 2 to the 4th is 16 times 9 gives me 144. That's the whole thing. And there's only one way to factor any number into primes. That's a fundamental, it's not the fundamental theorem of algebra, but it is a fundamental bit of algebra and how the real numbers work. Integers, by the way. Okay, so what they're asking is, so the biggest prime factor of 144 is 3, right? Because 3 is greater than 2. How the heck do we deal with something like this? Super tough. Do I know what 2 to the 12th is off the top of my head? I know 2 to the 10th is 1024, so twice that is 2048, and twice that is 4096. But suppose I don't know that. Pretend I don't know that. There's actually an easier way. Even if I do know that this is 4096 minus 1. So it's 4095. Then I got to do this nonsense. Do I really want to do this nonsense? I don't know. Okay, so I know that this is 4095, right? So I'll just write it up there. We'll keep track of it and see what happens. 4095. But what can we do here? How is this related to foiling and factoring? All right, it's related to factoring, isn't it? Because, well, we're factoring. You may remember when dealing with binomials and quadratics, we have a special thing. When we have a minus sign, a difference, and we have perfect squares. It's called, oddly enough, difference of squares, right? I know that if I have x squared minus 16, automatically this factors into x plus 4, x minus 4, right? Take the square root of this and put it here. I take the square root of this and put it here, and then I just do a plus and a minus. That's it. In the spirit of generalizing, in the same way we did the previous problem, let's generalize this a little bit more. I have x squared minus a squared. This factors into x plus a, x minus a, right? In this case, a is 4. Again, remembering this and this are numbers. This and this are always represent numbers in their place. So using the exact same generalization I used earlier, I can factor any difference of squares into this. Great. I have a difference of squares here. It's hard to see because of this. It's not something squared, is it? Let's recall one other thing. Let's recall our rules of exponents, right? And this I think might be Algebra 2, although I think it might be the tail end of Algebra 1 even. So again, these are like pretty fundamental concepts in algebra. We know that something squared is this, right? This is a different set of rules. We know that x to the a times x to the b is x to the a plus b. Right? We add the powers when the base is the same. But the other multiplying rule is this one, x to the a to the b. What the heck do we do there? Well, remember, we take these guys here and we multiply them. So this is x to the a times b. So if I have x squared cubed, I have x to the 2 times 3, 6. And why does that work, actually? Let's look at that one. X squared cubed. Let's just take the inside and use this rule for the inside. Right? If I have x squared cubed, I have x squared times x squared times x squared. Right? I have something cubed. It's something times itself 3 times. Now let's use this rule on these guys. Right? X to the a times x to the b. Well, a and b are equal here, but that doesn't matter. I take the powers and I add them. So this bit here gives me x to the 2 plus 2, which is 4, times x squared. Then I use this rule again. I add the exponents. X to the 4th times x squared is x to the 6th. The shortcut is you multiply the exponents. 2 times 3, 6. That's why this works. So, can I express this in terms of something squared minus 1? Using this rule, or this one. This is the generalized one, but let's think about these examples. So I want squared on the outside to give me 2 to the 12th. Right? Doesn't it stand to reason that I put x to the 6th in here to give me x to the 6th times 2? Something squared minus 1. All right? Something squared minus something else squared. This is 1 squared, right? Totally. Now, let's factor. Something squared. So I just take the something without the square, right? So that gives me x to the 6th and x to the 6th. And then the square root of this guy certainly is 1, whoops, and minus 1. Sweet. Okay, there you go. All right. But now let's use this. We're going to write this. We're going to write this using the actual numbers. So now I want to say that 2 to the 12th minus 1 is 2 to the 6th squared minus 1, which is 2 to the 6th plus 1, 2 to the 6th minus 1. Cool. So this is one factor, right? Can I factor this anymore? This goes in a red circle immediately, right? But I actually have another difference of squares here, don't I? I have something that I could think of as a power of 2. This is 2 to the 3rd to the 6th. Let's rewrite that. 2 to the 6th plus 1 times 2 to the 3rd plus 1 times 2 to the 3rd minus 1. All right, that's something squared. 2 to the 3rd times 2 to the 3rd. You add them, 2 to the 6th. Here's plus 1 times 2 to the 3rd minus 1 times 2 to the 3rd. Those go away, and then plus 1 times minus 1 is minus 1. Cool. Do I have anything else? Not really. So I would say this is probably good in terms of it being factored. But hey, now I can actually, these are all numbers. So I'm kind of done, right? Let's do it. So what does this equal? This is 2 to the 6th is 64. Two to the 3rd is 8. 8 plus 1, 9. And then 2 to the 3rd is 8 minus 1, 7. Not bad. This is 65 times 9 times 7. So this is like one of the levels of this thing. Except 7 is a prime number, so I get to circle it. But I need to factor 65 and 9. Right? So 65, my word. 65 is 5 times 13. These are both prime numbers. And then 9 is 3 times 3, and those are both prime numbers. Right? So I get to circle all of them. So I'm going to erase this and then bring this up here. Yeah, I'll just erase this part because this was the rules of exponents. So what we're saying is, I'll bring this up here, that 2 to the 12th minus 1 equals 3 squared, right? I have two 3's, so it's 3 squared times 5 times 13 times 7. Right. And the prime factors are 3, 5, 13, and 7. And actually, why don't I put them in numerical order? 7 and 13. All right? So what is the greatest prime factor of this number? Here it is. 13, right? 3, 5, 7, 13. That's the number. Did I pick up the calculator at all to do that? Rewind and check. I know I have to. But I'm pretty sure I did not do that. But what did I do? I actually used the difference of squares factoring trick twice here. I used it here initially. And then I found out that in the second step, I had another difference of squares that I could use. Then after that, I calculated the numbers. But again, I went from less convenient numbers to way more convenient numbers here. 2 cubed. Pretty sure you can do that. 2 times 2 times 2, 8. 2 to the 6th, it's a little bit of a stretch, but just keep going. I mean, 2 to the 3rd is 8, right? So 2 to the 6th is 2 to the 3rd times 2 to the 3rd, is it not? Because I added the exponents. So it's 8 times 8, 64. There's tons of ways to do these things. But I think the most interesting part is that I got to use a trick where I didn't have to go 2 times 2 times 2 times all the way up. I happened to know what it was, and I calculated it sort of quickly. Let's look at that in the calculator, actually. 2 to the 12th minus 1. Whoops, not in the exponent. 2 to the 12th minus 1. It is 4095. So it does make sense that 5 is a prime factor because any number that ends in 5 or 0 is divisible by 5. The divisibility trick for 3 is that all the digits add up to something divisible by 3. So 9 and 5 is 14, and 4 is 18. That's divisible by 3. That's why that guy is there. I don't know about 7 and 13. There's probably some rules for that. The number theory guys have that top of mind, and maybe somebody in the comments has the divisibility rules for 7 and 13. I feel like they're not very common. But that's it. Again, this is yet another way that you can apply something in mathematics to something that's an arithmetic question. And actually make it go quite quickly without picking up the calculator step by step. These are all really good exercises for your brain. Notice I didn't treat the numbers like as numbers in the parentheses. I could have added them here and here. I could have done that, but I decided not to. I kept on going. And then finally, when I could do no more, in terms of factoring, I actually then went to numbers. 64 plus 1, 9, 7, and then continued factoring in the conventional way. But again, factoring in the conventional way, because the numbers are way more convenient, right? 13 times 5, way more convenient than trying to factor, factor this. I could divide by 5. Man, what a nightmare. If I divide by 5, that means the other factors are 9, 7, and 13. How the heck would I come up with that? Not quite sure. But it turns out at the end here, I came up with 5, 13, 3 squared, and 7. Boom, done. Came up very quickly at the end here. All right, so that concludes the solution to these two problems. I could put whatever I want in here. It could be crazy. It could be an odd number in here. There could be all kinds of things, and just see if you can apply it using stuff that we actually know from algebra with symbols instead of the numbers. But the symbols always represent numbers. So if we operate on the symbols and find that easy to do, then we could actually plug numbers in and do something quite simple without picking up the calculator. I feel like that these days something that bugs me is a little bit of over-reliance on the calculator for simple calculations. And then if we had more questions where they were prefaced with without using a calculator, we'd be able to make these connections fairly quickly, or we'd at least really have to stretch and try to make connections between these two things. And I think that's super healthy, and then somebody who becomes good at math or good with numbers actually does these kinds of things. This might be a math Olympiad problem, something like that, but something where you'd run out of time. I think that's what it is. It's something where you run out of time doing this the conventional way, but if you do a trick, boom, it'll go quite quickly. All right, so that's a short one for today. Two things where foiling and factoring are not just for gibberish-looking symbols. They're actually useful when we deal with actual numbers in a problem. I just want to thank you for joining today. I feel like this topic is like super exciting and interesting. Please check back for more videos. Leave me a comment, leave me a like, subscribe, tell your friends, tell your terrible math teachers and your good ones. Tell them I'm helping, and I hope to see you next time. Thanks again for joining. I appreciate that. Take care.